So now we're gonna talk about some examples. So far we talked about a general framework of cubitization. So we learned about how this method works by drawing a connection with quantum signal processing, and then talking about a sort of a simplified version of cubitization, and then discussing the actual version that people discuss in the literature. And moreover, we have this very nice cost structure. And now the focus that I want to focus on a different question. So how do you actually implement this U of H? So obviously, this is a very important question if you're interested in doing practical quantum computation. So I'll consider an example. So because this course is about Hamiltonian simulation, I will again focus on the something that is related to the many-body system. So again, consider a toy model of fermions, which is locally interacting with each other on a one-dimensional line. Although I'm focusing on 1D models, generalizations to 2D is straightforward. And in this business, you usually map these fermions into quantum spin Hamiltonians, either using Jordan-Wagner transformation or some other more sophisticated transformations. So after you do that, you get a new Hamiltonian, which is nicely locally interacting in this 1D Hamiltonian. So now, obviously, the goal is to somehow understand how U of H works in this context. So remember, what we needed to do, at least what we wanted to do, was to find a U of H such that, let's see, if you apply this to some state G, lambda, then this is lambda GA lambda S plus that. And the first thing that we should do is to actually normalize the Hamiltonian properly, because this U of H, it must, in some basis, be in this block diagonal form. And obviously, U of H, it has a bounded, it has a norm which is a spectral norm bounded by 1. So if the norm of H is too large, then you won't be able to embed this into the unitary matrix while ensuring the norm condition. So what you would do, well, at least what I would do, is something like this. So we can first upper bound the norm of this guy by just using the triangle inequality. So suppose this sum ranges from 1 to n, and we use a periodic boundary condition, then individual terms such as xi plus 1, y plus 1, they have a norm of 1. So the total norm, it turns out, is upper bounded by t divided by 2 times n corresponding to x terms, n corresponding to y terms, plus believe this is that. Okay, so that's equal to n times the absolute value of t plus 3/4 that. Okay. So what I would do is that I just wanted to, let's see, I divide h by this thing. Well, actually, let's call this as alpha. Okay, so the alpha is an upper bound on H, spectral norm of H. So this we can safely say is less or equal to 1. So what we just do is that we normalize H by this alpha. Okay, and then what we realize is, as we discussed last time, that H is a linear combination of unitaries because all these terms such as xi plus 1, yi plus 1, zi plus 1, these are all just unitary operators. So we're going to leverage what we learned in these previous lectures in this cubitization setup. And once you realize that H is a linear combination of unitary, you can actually use the framework of select and prepare. So in select operation, at least in the context of cubitization, what you do is that you look at the Hamiltonian and just essentially write down all the terms in the Hamiltonian in a normalized way. So you just decompose the Hamiltonian into a linear combination of unitaries. And we see that there are a total of 4 n Pauli operators. And the select operation, which people often use this notation, cell H, acting on the ancillary system with an index K, let's see, and an arbitrary state psi on the system S acts as follows. So you simply apply the kth Pauli. Okay, the kth Pauli is just defined as follows. One might wonder how cheap this operation is. It turns out that the cost of select is order number of terms in the Hamiltonian. Which in our case is just linear in n. So we simply have a cost of order n in terms of 1 and 2 qubit gates. And then there was a prepare operation. And the prepare operation was the operation that encoded, prepare is a unitary operation that prepares a state that encodes information about these coefficients of the Hamiltonian. Okay. So what you might, so I think the notation for prepare is not as standard, but I'll just call them as prep H. And what you would want to do is that you apply this prepare operation on the ancillary qubits. And what you would like to get is, let's see. Right. Yes, I think this is the state that you want to get. So what is alpha? Actually, I need to properly normalize. Yeah. So what is alpha? vectoring. This is alpha 1 all the way to, sorry, alpha 0 all the way to alpha 4 minus 1, where these are the coefficients of these terms like xi plus 1, y plus 1, zi plus 1, zi. So to be more explicit, alpha k would be minus t over 2 for k from 0 to 2n, and let's see, u divided by 4 for k from 2n to 3n, and 1/2 of u for k from 3n to 4n. Okay, and you divide by this thing because, prep of h, it should be a unitary operator, so this state on the right hand side must be normalized. Okay, so that's prepare of h. And we've already done a similar algebra a couple of lectures ago. And we're just gonna repeat the same algebra. I mean, it's basically the same idea. And the idea is the following. So suppose we apply prep of h and cell of h, select of h, and prep of h dagger 1, 0. This thing. And we're going to just apply, and we're going to just apply the bra 0 on the left-hand side because that will make our life slightly easier. So, of course, prep of h is just, if you apply that to the 0 state, this just becomes alpha k divided by this thing. So if you apply the cell of h to that, well, you simply get this linear combination. Oh, sorry, I think, yeah, so there was a square root here, and I forgot to add that. But then I think, sorry for messing this up, but I think if there's a square root there, I think there shouldn't be a square root here. Actually, there should be. Yes. Okay. Good. And now, well, of course, we can apply this operation, just view from bra instead of cat. And then we can apply this operation from the left-hand side, and that leads to the following identity. This is equal to k alpha k absolute value pk psi of s. Okay, so what this means is that Right. If you apply pref h dagger, cell h, pref h to this fixed state, 0 state, applied to psi, this is simply that thing times, let's say, so this is, I realize that this is not exactly the Hamiltonian I want, and I'll explain how we can fix it. But we have this operator acting on this state plus some other state. Let's call it as G psi perpendicular. And this is not, in general, not a normalized state. But what we can ensure is that if you take the inner product of this G psi perpendicular with the 0 state on the ancilla, they will be orthogonal to each other. Because according to this calculation, if we apply the 0 state, bra 0 on the left-hand side of this expression, then, the bra applied to this guy should be equal to the bra applied to this guy. So the bra applied to that guy must necessarily be 0. So in that sense, at least for a Hamiltonian simulation, it's rarely the case that ensuring this orthogonal junk is a problem. Easily, these are like automatically taken care of. Okay. Any questions at this point? Okay, so I'll continue. So one thing that you may worry about at this point is that this operator that we got is not really the operator that we wanted to implement, right? So we define prepare and the select operation, and at the end of all of that, we obtained this equality. But you see, the actual Hamiltonian is this thing. Well, okay, so maybe it's not exactly that, but certainly it is proportional to this sum of alpha k pk. And clearly, once we take the absolute value, that will in general be a completely different Hamiltonian. These two will be equal to each other up to a proportionality constant only if u is non-negative and t is non-positive. So only in that case, these two will be the same. So how do we deal with this problem? So it turns out that there's a very easy solution. And the solution is to simply redefine your Pauli operators. So remember, in this linear combination of unitary business, it didn't really matter whether the unitary that you defined had a minus sign or not. As long as it's a unitary, you're good to go, basically. So at the high level, what you only need to do is to simply declare that, well, for, let's see, so depending on the sign of t, you either declare a sign of -1 to the a, or -1 or +1. And wherein this, the sign depends on the sign of t. And similarly, depending on the sign of u, you just change the sign of zi +1 or zi. So that's an easy solution. And the extra cost that you have to do because of this is pretty minimal. So to be concrete, let's say hypothetically, actually not hypothetically, for concreteness, suppose I already had a circuit that implemented this operation. So let's see. So let's say I have a single qubit such that if the first qubit, so this is a qubit, and this is a, let's say, some system consisting of more than one qubit. And if the single qubit is in the 0 state, you don't do anything. If the single qubit is in 1 state, then you apply, let's say, pk psi. Okay, and all you need to do is, let's say you want to apply minus pk psi, and then instead of that, all you need, let's call this unitary as just u. Okay, all you need to do is that you change u into u to zq u, because then if you're in the zero state, then you again do nothing. And if it's in the 1 state, then you get a minus sign because you apply zq on the first qubit, and you still apply this Pauli that you want. So as you see, all you need to do is to just add a single qubit unitary, single phase operator, and that's an extremely cheap thing. So for this reason, if you look at the papers, more recent papers, well, maybe not even the more recent papers. If you look at papers on qubitization for Hamiltonian simulation, without loss of generality, you always assume that these alpha k's, these coefficients, are non-negative, because you're not losing much generality. If alpha k is -1 in practice, you just add an extra phase k somewhere in the middle of the computation, and that rarely changes the end conclusion. So with this, you can see that although I discussed a very simplistic example, I hope it's clear how this picture will generalize to a more realistic Hamiltonian. Let's say when you have a long-range Coulomb interaction, or if you have a complicated quantum chemistry Hamiltonian, wherein you have essentially all-to-all interacting Hamiltonian. In that case, well, you have a more complicated form of the Hamiltonian. You have like not just xi plus 1, yi plus 1. You have a Pauli operator, which may be very high rate, because maybe you want to apply the Jordan-Wigner transformation. But even in that case, well, this select operation is a very simple thing. You just apply a Pauli operator depending on the index. And the prepare operation is also, it doesn't really care about how complicated the Pauli operator is, because prepare operation, that just encodes the information about the coefficients of the Hamiltonian, not the actual operators. So yeah. Good. So I wanted to give you more like a global picture on how the qubitization looks like in the grand scheme of things. And it roughly looks the following. So yeah, maybe I should have added this picture that I've been showing probably like 10 times. So of course, in the grand scheme of things, we have things like Z phi 0, Z phi 1, Z phi 2, and these things, okay, so, and in between, you're interleaving this W of H. And this upper part, this acts on the ancilla, and this lower part, this is the part that acts on the system, okay? And if you look into this WH further, you can decompose into like a sequence of unitary of H and unitary control unitary of H dagger and the control unitary of H, and just some single qubit operations. And if you look into U of H, then you see internally, you see these things, such as prepare of H and select of H. At least if your goal is to do like a Hamiltonian simulation. And in all these things, remember that these Hadamard, X Hadamard, these are very cheap operations. So they don't really add too much to the overall cost. And when you apply this, well, imagine plugging in this U of H into this controlled version, okay? In that case, it's not too hard to see that the select operation, for instance, will be the controlled select operation, controlled on a single qubit. And the prepare operation will be just a controlled prepare operation. So in the grand scheme of things, the overall cost of the qubitization can be, for Hamiltonian simulation, can be roughly thought as 4 times the control preparation, because, you know, each U of H, you apply prepare twice, and you get like 2 controlled select operation, because you get one here and another one here, times the degree of the polynomial. So this would be, if you can figure out the cost of applying a controlled prep or a controlled select operation accurately, then you get a pretty good idea on what kind of cost of quantum algorithm, what kind of cost you need to run your quantum algorithm. Okay, and I should mention at this point that while my focus was on Hamiltonian simulation, this select plus prepare framework is very useful in the, well, okay, so that is very useful, but there are other encoding schemes. So just to reiterate, so what we did was that we constructed WH such that if you apply this to state, then you get, well, this desired operation. But and in order to construct this W of H, we used select and prepare. But it's important to realize that that's not the only way. I mean, for now, this is like the go-to method for Hamiltonian simulation. But in the future, maybe somebody will come up with a better method, better framework. So, and I just wanted to point out that there are other ways to encode a matrix into a unitary, and these were not developed in the context of Hamiltonian simulation. Rather, they were developed in the context of other things, such as quantum machine learning algorithm or solving systems of linear equation type of business. And they are, whether they'll turn out to, whether they will be useful or not in the future is an open problem, but certainly, at least theoretically, they're very interesting. So let me just tell you about one example, which is not about Hamiltonian simulation. And this is, it's kind of a very weird thing, but it turns out that you can do things like this. So suppose we have an arbitrary quantum state, what we want to do is that we want to evolve this by some density matrix. And this density matrix sigma is, it can be anything as long as it is easy to prepare its purification. Okay, and this looks like a very strange thing. I mean, density matrix, it's not really a local Hamiltonian. I mean, think of sigma as like maybe like the Gibbs state of some locally interacting Hamiltonian. In that case, this will not be some locally interacting Hamiltonian. In that case, this would be like an exponential of some locally interacting Hamiltonian. It's a very strange object. But in the context of quantum principal component analysis or other quantum machine learning algorithms, these are subroutines that are useful. And it's interesting to notice that using qubitization, you can also very straightforwardly implement this kind of operation. So how this works is the following. So what you do is the following. So suppose by our hypothesis that there is a unitary such that if you apply on the simple state, let's say A1, A2, so we're imagining decomposing this ancillary system into A1 and A2 such that let's see. If we trace out A2, then we get this sigma on A1. Okay. Then what you can do is that you apply this unitary on this state, and let's say we have a target state that we want to play with, let's say psi, and then what we do is that we apply a swap operation between A2 and S. And it turns out that this is actually equal to U A1, A2 plus some, let's see, let's call this as sum jump. So this is some state which is orthogonal to this guy. And the algebra is very simple. I encourage you to work it out. But just to give you the basic idea, the idea is to compute the following thing. So as in the Hamiltonian simulation, imagine taking the raw version of this thing on the left-hand side, on both sides. And then imagine just, oh, sorry, yeah. Imagine computing this thing. And pictorially, what this amounts to is the following. So this guy is just you apply to A1, A2, and the thing over here is just a broad version of that. And so there you have it. And we have psi over S. Okay. And we have A1, A2, S. And swap operation just swaps A2 and S. And pictorially, that amounts to having this crossing link. So what you end up having is this operation. And that's just, if you rearrange the diagram, then this turns out to be actually equal to sigma applied to psi. Okay. The basic point is that if you look at this part, enclosed in this region, this is basically just a density matrix. So you end up getting this identity. So the point that I guess I'm trying to emphasize here is that cubitization is a very flexible framework. Even though we talked about Hamiltonian simulation, you can do these other things. Not just Hamiltonian simulation for like physical Hamiltonians, but like somewhat very strange unphysical Hamiltonians. And yeah, so let me again emphasize that quantum machine learning algorithms, we currently do not know if they will be useful, but these ideas are certainly interesting. But at the very least, what I can say is this. So by using these more flexible versions, versions of cubitization, we can actually...
yeah. May I ask a simple question?
Yeah.
So when you say there's a flexibility in this cubitization scheme, can you, are you saying that other than the Hamiltonian like object, which are Hermitian operators, Hermitian matrices, maybe can you do something useful with non-Hermitian matrices or non-Hermitian operators?
There is a framework. So next time I will briefly discuss about what is known as quantum singular value decomposition. And singular value decomposition is given a general matrix A, just yeah. So this is a diagonal matrix. These are two unitary matrices. So you can play the same game with the non-Hermitian matrix like this, and majority of the things carry over. Is there a killer application of quantum singular value decomposition? I'm not completely sure, but you can do it. So it'll be cool if somebody can come up with a cool application of this quantum singular value decomposition.
Okay, thank you.
Yeah. And maybe let me just add one more thing. So which is that there's a well-known trick to deal with non-Hermitian matrices. So for instance, like in this Harrow, Hasidim, Lloyd paper, so they do consider like a general non-Hermitian matrix. What I mean by that is the goal is to solve this equation where you don't have any constraint on A. So I mean, it has to be invertible, but A doesn't have to be Hermitian. And the well-known trick is that you can always construct the following matrix. Let's say A prime, which is a Hermitian matrix no matter what. And what you can do is that you can simply solve AX equals B by solving A prime X equals B prime, where B prime is related to B in a very simple way. So there are these tricks that people know. Anyway, it was a bit of a tangent. Okay. All right. So yeah, the important point that I want to emphasize is that these weird time evolutions, even for quantum simulation, they're actually very useful. So at this point, I guess it's not too surprising that these, I don't know, very weird ideas like linear combination of unitaries are actually better than like the naive like nature mimicking methods like Trotter Suzuki methods. But there's another layer of surprising thing here, which is that for the purpose of quantum phase estimation, it turns out that it's actually much better to compute to not use the time evolution, but instead use the time evolution by some weird Hamiltonian. So let me recall. So in case you forgot, quantum phase estimation, what it does is the following. So if you have infinite precision, so let's say you have a general quantum state, I psi I, where these are the eigenstates of H, then you apply quantum phase estimation, and then you get eigenstate psi I with probability alpha I square. And the ingredient that goes into quantum phase estimation is the time evolution. So if you can implement this time evolution operator, you can leverage this to perform quantum phase estimation. And I told you that this has lots of applications, including eigenvalue estimation, which is energy estimation in this case, and also like eigenstate preparation. And I believe I also said that because of this, the better you can do Hamiltonian simulation, the better the quantum phase estimation will be. And that's certainly true. But it turns out that because of this development in qubitization, that there was actually like a new shortcut was discovered to perform quantum phase estimation. And the idea is to avoid applying this time evolution by the original Hamiltonian, but instead consider a time evolution by this weird Hamiltonian, okay? So remember this H, we already normalized such that the spectral norm of this thing is like less or equal to 1. So this inverse cosine is well defined. And the point is, if you, this is, let's see. So this is cosine minus h plus y sine cosine minus h. So that's plus square root of I minus h squared. And it turns out that actually implementing this kind of time evolution is much easier on using qubitization. In fact, you know, like if you want to implement e to the minus iht using qubitization, you have to use this Jacobi-Anger approximation to approximate this e to the minus iht by like by a polynomial. But for qubitization, time evolution by this thing, this can be implemented exactly with just like no approximation. So, and moreover, okay, so h and r cosine h, I mean, obviously they are different things, but they're essentially related in a very intimate way. So when it comes down to the eigenvalues, they're related by lambda and inverse cosine lambda. But that's a very simple function that you can implement classically. So to estimate the eigenvalues of h, you just do time evolution by this thing. And then once you measure the eigenvalues of that thing, you just apply inverse cosine of that thing. It's a very simple classical process. I mean, you can do it on your laptop. And moreover, their eigenstates are also the same. So h and r cosine h, they just share the same eigenstates. So for preparing eigenstates, this is also more efficient. So this was discovered by, to the best of my knowledge, these two different groups of folks in 2017. So it's a little trick, but it's a very useful trick. And all the known state-of-the-art methods for quantum chemistry simulation using fault-tolerant quantum algorithms, they all employ this result in one way or another. So this is another indication that you can be creative and do things that nature doesn't do, and that can actually be better than the naive methods. Okay, so to summarize, I hope I was able to convey that qubitization is a very flexible modern framework for developing quantum algorithms, because you can consider many different input models for the unitary encoding, such as select term prepare or density matrix or other things. While the unitary encoding we discussed last time was somewhat simplistic, I think that's like the simplest version of qubitization, which sort of tells you the technical details on how everything works out. So that is too simplistic, but with some minor modifications as we discussed today, you can essentially restore all the nice properties. Well, actually, it makes it even better, because with the discussion today we had today, we can have a much more flexible form for qubitization. And if you look at the recent literature, there's a lot of activities, but in a way, they're all like how should I say this? In a way, they are all, the improvements are made in a similar way, in a sense that improvements are not made in the qubitization. So that part is like already done. What is being done is improving the efficiencies of these select and prepare subroutines. So, and the main theme there is that oftentimes the Hamiltonian has a special structure, and you can exploit those special structures to reduce the cost of these select and preparation subroutines. So identifying such structure seems to have a direct application for making the quantum algorithms more efficient. Okay, so that's it for today, and I'll take some questions.
Okay, so if there was a sort of alternative universe where the time evolution of a physical state took place according to E of I times inverse cosine of H times the time, then the Schrodinger equation would have inverse cosine H acting on the wave function. Which means that the wave function may not be the best way to describe the physical system, physical state, but I don't know. You have to do something to get rid of the inverse cosine in the Schrodinger equation.
Yeah, I'm not sure if it's easy to do that.
Yeah, so maybe it's not so easy to invent such an alternative universe. Yeah, okay. So maybe this is really something invented by a human.
I think so, yeah. I think so.
Okay. Do we have any questions from students? I can even give out some, gifts or prizes on behalf of our speaker for good questions by the students.
Well, you can always ask me through email.
Yeah.
I believe, yeah, my email is available. So I'll be happy to answer questions.
Can we have like a 2-minute preview of what's to come in the next final set of
Sure, yeah. So next time it'll be more of a survey. So I think I will discuss roughly half about quantum singular value decomposition and also like variational quantum algorithms. And I guess for variational quantum algorithms, I guess that there isn't, mm, let's see. So I do want to make some comparison between the variational quantum algorithms and these fault-tolerant quantum algorithms, and particular about what their pros and cons are and what kind of open problems there are. Yeah, so it'll be mostly a survey. So I will go into much less detail next time.
Mm. Okay, so if no further questions, let's share some words of thanks to the speaker for another round of excellent and instructive lectures. Thank you.
Thanks. Bye.